circle, Peter, the kite, right there, then where's the star go? Oh, hurry, 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 where does the star go? Man, so close that time.
Hey, Noah, what are you up to?
Oh, hey, Pete. I was just cleaning out our games cabinet and found this old Perfection game from when I was a kid.
Oh, I remember that game. That's the one where you have to put all of the plastic pieces into the holes, right, in the board, and to get the shapes to line up before the timer goes off?
Right, yeah, exactly. And if memory serves, I used to be a lot better at it than I apparently am right now. I keep trying to put some of these pieces into holes that are similar, but not quite right, and I'm just not able to get them all in place before the board pops up at the end of time.
Well, it's too bad you can't use topological deformations with these plastic pieces. That'd make this game so much easier because, topologically speaking, these are all the same shape.
What? How does that work? I never studied topology, so I don't know what these deformations you're talking about even are.
Oh, really? Well, when I was teaching at UW, I actually taught a course in topology. I think you'd probably find some of it pretty interesting.
Do tell.
Okay, well, to start off, consider this question. How do you know a shape?
How do I know a shape? Well, usually I look at it, and because I've graduated from kindergarten, I know what it is.
I see. So you're thinking like parallelograms and rhombuses and all that, right?
Well, I was more thinking circles and triangles if I'm talking about kindergarten. I don't know if I got into parallelograms and rhombuses until first grade.
Okay, I hear what you're saying. Let me ask the question in a slightly different way. I want you to think, how do you know a shape in the same way you might ask the question, how do you know a person?
Oh, you mean like what are some things about the shape that I know?
Yeah, what are some deep things that you know about the shape?
Well, I'm not sure if this is what you're getting at, but I can tell you how many sides or how many angles a shape has. I can tell you whether it's an open shape or a closed shape. Is that the kind of thing you mean?
Yeah, that's good. So when it comes to topology, and in particular when it comes to deformations, we want to think about how we know shapes in terms of the relationships they have with other shapes. Are two shapes similar enough that one could be molded and bent and cajoled so that it appeared to be the same as the other shape? Or is there some way in which two shapes are really fundamentally different? In the game of perfection that you're playing, none of the shapes really are fundamentally different. They're all, topologically speaking, the same.
Well, that's confusing to me because I'm looking at these shapes and some of them look like stars, some of them look like the letter S, some of them look like geometric polygons like a square and a rhombus. How are those the same shape?
Well, let me tell you an old joke that I know that will shed some light on this. And it goes like this. How can you tell that someone is a topologist? I don't know how. They can't tell the difference between a donut and a coffee cup. Nothing, huh? No laugh?
Okay, all right. Let me make you a promise. The reason I didn't laugh at your joke was not because it's not funny, but it's just because I don't think I have the context or the understanding yet. So why don't you tell me that joke again at the end and we'll see what happens.
All right, fair enough. So let me tell you what this joke is based on. It's the idea that a coffee cup can be continuously deformed into a donut. So imagine you've molded a block of clay into the shape of a coffee cup. You've shaped the cup that will hold the liquid, and you've attached a handle to hold it. But while the clay is still wet, you decide, nah, I'd rather make a donut because donuts are more delicious. So can you deform the clay into the shape of a donut without splitting the clay into multiple pieces or breaking the handle?
Oh, sure. I think I see what you mean because there's already a hole in it in the handle. And so all I would have to do would be to kind of shift some of the clay from the cup part around into the handle part and make it more even around the hole, and I'd have a donut.
Yep, you got it. That's right. Also, notice I used a very topological word when describing how we made the coffee cup in the first place. We attached a handle. So this is the essence of topology. You study shapes that are made like art projects by gluing and attaching and folding and twisting. And then you allow deformations to take place.
Oh, okay, I get it. So are all of these shapes part of breakfast, like donuts and coffee, or do topologists do lunch and dinner too?
We eat 3 meals a day like the rest of you guys, but why don't we take a step back and kind of look at an overview of some of the shapes, I might call them spaces, that we look at in topology. Some of these will be very familiar. You know them quite well. In fact, you already named them, like the circle. That's a very familiar shape. How about this? Just the real number line, which is, you think of it as the ordinary x-axis, or the real plane, which is the ordinary xy plane. You mentioned the circle. Let's go ahead and add the sphere. Those are all very familiar.
Okay, but hold on. The number line counts as a shape in topology?
Well, yeah, it's a line, right? It's sort of the basic model of all lines. Every line looks just like the real number line, right?
So you just meant a one-dimensional line. I was picturing the line with all the little hash marks and the numbers written up above it as the number line.
No, we could do that, but then we're talking about something different. So here's one that is a lot of fun to build as a home project or in a classroom that is really important in topology. It's the Mobius strip. Start with a long rectangular strip, maybe cut a piece of construction paper the long way, not too wide. Now imagine you're going to curl it up and attach the two ends together, but before you do it, you put a twist in it and then you glue the ends together. What you get is a space, a shape, and it's called the Mobius strip.
I'm actually already a little bit familiar with the Mobius strip. In fact, it reminds me that back when I used to do Photoshop contests, one week the contest prompt was to design the worst amusement park ride imaginable. And I took a roller coaster and put a half twist into the track and made a Mobius loop that would be a never-ending roller coaster ride, which I think would be pretty horrifying. And I called it the Mobius trip.
Oh, I love that. You know what's funny? I don't think you knew this, but my thesis advisor in graduate school used to talk all the time about how we need topologically themed amusement parks. And he had all these rides that he would talk about. One was called the Hop Rotator. Yours, the Mobius strip, would be right at home in this park. Hey, Math Club. This is Pete with a personal note about today's episode. I'd like to dedicate it to the memory of Steve Mitchell, my thesis advisor at the University of Washington. In addition to being an outstanding topologist and beloved teacher, Steve was a very important friend to me and my family. Not a day goes by when I don't think about the time he and I spent together. I miss you, Steve. This one's for you. And so we could go on creating lots and lots of other spaces. Like, for example, imagine that you've got some kind of floppy, pliable, stretchy material, and it's shaped like a rectangle. You fold it up and glue two of the edges together so that what you now have is a cylinder. And on either end of the cylinder are circles. The boundaries are circles. So what if you took that cylindrical tube and curved it around so that you could join the circles together and glue them to each other?
Oh, making a torus.
Making a torus, right? Like the shape of an inner tube.
Kind of like our donut that we were talking about earlier.
Kind of like our donut. The only difference is the donut from before is a solid torus. It would be full inside with moist, cakey goodness. And jelly. And jelly. So the torus itself has sort of an empty air hole inside, like an actual inner tube. A solid torus is what would model a donut. So these are the kinds of spaces that we think about all the time in topology.
Okay, I'm with you so far, but I also have to say that so far this sounds a lot like geometry, but it must be different in some way, or it would just be called geometry, right?
Yeah, you're right. And in geometry, we use measurements to study shapes, right? The word geometry even tells us this. So geo meaning earth and metry meaning measurement. So for example, every triangle has 3 corners. Every triangle has 3 sides.
No more, no less. You don't have to guess.
And each side has a length. In fact, each corner defines an angle, which spans some number of degrees. You get the picture, right? There's a lot of measurements going on.
And a circle has a diameter and a circumference.
Exactly. So geometry places a very strong emphasis on measurement. But what if we throw that notion out so that we have no idea about distances, areas or volumes. What can we say about shapes then? That's where topology comes in.
Okay. I think you better give us an example.
I think so too. So let's consider a balloon. We blow air into it, and now I'm just going to hold it closed. And I want to think about some of the questions that a geometer might ask about this balloon full of air.
So wait, just to be clear, a geometer is a mathematician who specializes in geometry?
You got it. That's exactly right. And they might ask questions like this. What's the surface area of the balloon? Or what's the volume captured inside the balloon? Now, if we let some air out, then both of those particular measurements will change, right? The surface area will decrease, the volume inside will decrease. Any other measurement that we make about the balloon, it will decrease as well. But there are some things that do not change when I let some air out of the balloon. For example, the fact that the balloon separates space into two parts, the part enclosed inside the balloon and the part outside the balloon, right? That's going to stay the same. Also, the fact that the balloon consists of a single piece itself is just one component. That doesn't change when the balloon blows out or shrinks down.
So is one way that a topologist distinguishes between shapes and identifies them either as being the same or different might be how many separate sections that shape divides space up into? Like the balloon would divide space up into two different sections, but if you slice the balloon open, it no longer would have any space contained within it. So now it would be different.
Yes, exactly. Similarly, suppose you get out a piece of paper and you draw a circle on it. Now you've divided the paper into two components, the part inside the circle and the part outside the circle. In both of those cases, there's an inside and an outside, but dimension plays a part of it. The region enclosed by a circle is part of a two-dimensional plane, whereas inside our balloon, which is really a model for a sphere, what's inside is a chunk of three-dimensional space. So yes, there's an inside and an outside. There's something like a hole involved, but they're not the same hole. The holes have different dimensions. And that turns out to be really important in the story of topology. How do you find holes? And what dimensions do those holes have? The act of letting air out of the balloon and then closing it back up again is a kind of continuous deformation. That's the sort of thing that we're interested in largely in studying in topology.
Okay, I think I'm starting to get it. So just like letting the air out of the balloon was a kind of a deformation, we could take all of those pieces from the perfection game and either inflate them up or deflate them down, or like with the coffee cup before, we could kind of move the clay around a bit. And that's what you meant when you said all of those shapes were essentially the same, that one of them could be deformed that way into any of the other shapes that are in the game, right?
Exactly. So let's push on that a little bit. And let me ask you to think about the letters of the alphabet. And for the sake of nailing it down, let's picture in our mind's eye just the capital letters of the English alphabet. So we've got 26 different letters. I'd like to know which of these letters can be deformed one into the other and which ones cannot, so that we can group the letters of the alphabet into subsets of letters that are all equivalent to each other. For starters, what letters do you think you can create if you start from the letter C?
Okay, so I'm picturing that the letter C is made out of something malleable, like clay or like a pipe cleaner, and that all I can do is just sort of deform it. So
Yep.
I guess the easiest one that pops into my head first is that I could deform the C into the capital U. They're almost the same shape already. All I would have to do would be rotate it 90 degrees and kind of flatten out the bulges on the left and right edge, and I would have a U. Is that what you mean? Am I doing this right?
Exactly. All right. C and U, they are topologically equivalent.
And once I have the U, it's pretty easy to deform that into a V. All I have to do is kind of take those two sides and turn them both into straight lines that intersect at the bottom. So is V also the same as C?
It is.
Okay, this is kind of fun. I think from there, I could take the V and completely straighten it out into a capital I. Not the kind of I that has the serifs at the top and the bottom, but just the capital I that's just a straight line.
Exactly, you could. All right, I am pretty confident that you could find all of the letters that are equivalent to the C. So that's going to form one group of letters. I'll just read them off real quick. C, G, I, J, L, M, N, S, U, V, W, Z.
Wow, there's a lot of them in that first group. I have to assume that not all of the groups are going to have that many letters in them.
You are right. That is the largest of all of the groups. Let's try one that has fewer elements in it. How about starting with the letter D?
Okay, so the letter D, first of all, I could deform it into the letter O. It's almost already the same shape. And then I could also deform it into, I don't think I can think of another one. Would the Q be the same, or is that something else?
Well, that's a really good question. The Q certainly has a circular aspect to it. However, the Q has that little foot or that little tail, that little line segment that crosses over the circle. So they are not going to be the same. We would not be able to create a Q from either the letter D or the letter O.
Okay, but why couldn't I just kind of fold that tail right into the round part of the letter, smushing them together and making it into the O?
You could do that, but it involves a more subtle kind of topological equivalence called homotopy equivalence. The kind of equivalence we're talking about here is a bit stricter. So to see why the Q and the O are different, notice that the Q contains a very special point. That point where the circle and the line segment intersect, if you remove that point, it separates the Q into three pieces.
Oh, so if I'm picturing this right, removing that point would leave you with a C shape and then two little straight lines, right?
Right. But neither the O nor the D has a point with that property. If you remove a point from either of those letters, what you're left with is a single connected shape that's equivalent to a capital C.
Okay, I get it now.
And just in case listeners are wondering, reminder, we're just talking about capital letters. Certainly a lowercase d is going to look different from a capital D and will not be the same as an O. I think you have found the only two in this equivalence class, the only two shapes that belong together, D and O.
All right, that was another easy one. Give me one that's a little bit more difficult.
Okay. How about this one? Why don't you start with a capital F?
So the capital F has a right angle, and then it kind of has another little piece coming off it in the middle, almost like the Q does that we were just talking about. It has an extra little tail. So I'm looking for a piece that has a right angle and another little bit, maybe a T, a capital T, that kind of has a right angle in it and then another little piece attached to that piece. Would that be the same?
Yeah, in fact, it would be. If you took the top bar, the hat, so to speak, of the F, and just kind of straightened it out, and you just left its little nose sticking out, then that is very similar to a T. It's a line segment with a little piece sticking out. Sure, a T is maybe proportioned differently, but that's okay. Compress, smush, stretch, boom.
Okay, but the way you just described that made me realize that even though I got the answer right, I think my reasoning for why the F and the T were similar was maybe not exactly right. It had nothing to do with them both having a right angle, did it?
No, and in fact, a right angle is an angle that has 90 degrees in it. So we would have to make a measurement to figure that out, and topology has no mechanism for measurement.
I just threw that out there for all the geometers in the audience.
Those are the guys and the gals that do geometry.
Right. Okay, so if I think again about a line segment then that has another piece coming off of it, kind of like the T does, the capital Y would be pretty similar, wouldn't it?
Yeah. In fact, why don't you explain how you would deform a T into a Y?
Well, I think I would just take what you call the hat of the T and bend it. So instead of them being perpendicular to the other part of the T, the vertical crossbar, they would each be kind of going up at a 45-degree angle.
Exactly.
I think that's maybe it for this group. I don't think I can think of another one that would go into this group.
Well, there is one more. It's something that we haven't hit on yet that I think if you go back to the F and look for another kind of deformation on it, you'll arrive at this final letter.
Oh. And I don't mean oh. I mean, oh, you're talking about a capital E. I could turn a capital F into a capital E by taking the bottom piece and just kind of bending it a little at a 90-degree angle.
Yeah, you would give it a foot, right? And an E is like an F with a foot. And by the way, this very metaphorical and visual language is part and parcel of the topologist's toolbox. We often use very suggestive, very visual language when describing any shape or space that we're thinking about. So when I say things like, oh, the F has a hat, or give it a foot, or now it's got a nose, I am deliberately using that language because I'm trying to help drive home that the world that is familiar to us is also present within the topological world. We just have to draw it out with our language. So let me give you yet another useful metaphor when thinking about topology. I want you to imagine a pair of glasses. These are going to be very special glasses. In fact, I'll call them topological glasses.
Are these glasses like the coffee mug we were talking about at the beginning? Or do you mean glasses like that you look through?
The kind that you look through. So maybe we should call them spectacles. That might make it like the topologist's spectacles.
I think that was one of the titles that J.K. Rowling was considering for one of the Harry Potter novels, was Harry Potter and the Topological Spectacles.
You know, you can't help but make a spectacle of yourself, can you? So these spectacles have a very special property. While you are wearing them, any two shapes that are topologically equivalent look the same to you. You no longer are able to distinguish them when you're wearing your glasses.
So these spectacles would not make for a good pair of reading glasses, considering what we just said about all of the different capital letters.
Right. In fact, once you put these glasses on, as far as you know, there are only 10 letters in the alphabet. So you would have far fewer words to read with. That's exactly right. Good. Now, what these glasses illustrate is pretty much the central problem in topology, which is the classification problem. Given two spaces, can you tell whether or not they're equivalent? In other words, can you tell whether or not they will look the same once you don this pair of topologist spectacles? And that impulse to classify is very similar to what, say, a scientist would do. Chemists classify elements in the periodic table. Biologists classify the world of life sciences. Zoologists classify zoos? No, animals. And
okay, but unless I'm just completely out of the latest technology loop, there's no such thing as topological spectacles. So how do you actually go about telling spaces apart in topology?
let's focus on two particular topological spaces and ask whether or not these are the same, and then talk about a way to show whether, in fact, they are or are not the same. Okay? And the two spaces I have in mind are, on the one hand, the sphere, which you can think of as being a beach ball, and on the other hand, the torus, which you can think of as an inner tube or the surface of a donut.
Okay, so I've got these two mental images, and what we're about to do is we're going to try to figure out if there's a way to deform one of them into the other.
Yeah, so first, what do you think the answer is?
Well, I think the answer might be no, because the torus has a hole in the middle and the sphere doesn't. And in order to make them identical, I would kind of have to puncture a hole into the sphere, and I don't think I'm allowed to do that.
Right. And in fact, the sphere also has a hole inside it. It's the inner space, right? That's the kind of hole that the sphere has. And the torus also has something like that. Namely, it's got an inside that also encloses space, but those two insides seem different. And as you mentioned, the torus also has this other hole where you could put your arm through it and kind of wing it around, right? Like a hula hoop sort of thing. So intuition says we probably cannot deform the one into the other, right?
Right.
So what we need is a mechanism of some kind that allows us to distinguish between different spaces. The simplest object that we could attach to a surface or a space or a shape is a number. Ideally, this number would have the property that two spaces that cannot be deformed one into another would have different numbers. If I can find a way to attach a number to a shape, and then for different shapes, compare the values of those numbers, we'd be in business.
Has anybody found a method to break a shape down into just kind of one single topological number that allows you to do this?
In fact, somebody has, and that somebody is Leonard Euler.
You mean Leonard Euler of the Houston Oilers?
Oh, yeah. Didn't I tell you we're switching over to the football club podcast now? Wait, the Oilers is a football team, right?
All right. Just go on with your story.
Right. So here's how we calculate this number. So I want to take the sphere and I want to subdivide it into triangles. I want to imagine something like, have you seen the giant sphere, the tessellated sphere at Epcot Center before?
Yeah, I can picture it. It's like a giant sphere that's made out of hundreds of triangles.
Right, exactly. Now, we want to imagine doing that same kind of triangulation to both the sphere and the torus. So imagine that we are drawing triangles on the surfaces of both of these shapes, and we have a couple of rules that we have to follow. So the triangles can't overlap in some willy-nilly way. Each adjacent pair of triangles has to line up edge to edge perfectly. And then we just keep tessellating as we go around until we have completely covered the surface with triangles. Okay?
So we're doing that to the sphere, and we're also doing it next door to the torus.
Exactly. Now, for the sphere, we have some number of triangles on the surface, and we have some number of edges. Those are the places where the triangles join right next to each other. We also have a number of vertices. Those are the corner points where some number of triangles come together and meet at a single point. So here's what we calculate. The number of vertices minus the number of edges, and add to that the number of triangular faces. So 3 different calculations get brought together. For short, we might say V minus E plus F. That quantity is known as the Euler characteristic.
And then when we do that to our sphere, we're going to get a certain number. And is what you're telling me, if the sphere were able to be topologically deformed into the torus, then when we did the same thing to the torus, we would get the same number, the same Euler number?
That's exactly right. Yeah. Now, to do this, you actually need real triangulations. We would need to get out a sphere and draw on it, or get out a torus and draw on it. But fortunately, there are a couple of models that we can turn to. Have you ever played Dungeons and Dragons?
Oh, sure. Yeah.
Okay. So the dice that are used are solid, but on their surface, they actually give a model for spheres. In fact, the icosahedron is a perfect example of this. So the 20-sided die, its surface gives a perfect model for how we could triangulate a sphere. The question is, how many faces, edges, and vertices does a 20-sided die have?
Well, I know it has 20 faces. I'm going to take the easy one, and I'm going to let you tell me how many edges and vertices it has.
Okay. All right. I'll do the hard work of figuring out how many edges and how many vertices they are. So let's see. A quick mental calculation. 1, 2, 3, 4, 5 divided by 2 and square root of 7. Okay. So there are 30 edges on an icosahedron. If you happen to have some D&D dice lying around, go ahead, pick it up and count. You'll get 30 edges. And there are 12 vertices. Okay. So we have 20 faces, 30 edges, and 12 vertices. If we perform the calculation, vertices minus edges plus faces, we end up with 12 minus 30 plus 20. Care to take a stab at what that is?
Is that 2?
It is 2.
Did we only get a 2 because we triangulated the sphere with 20 triangles? Like, what if we had triangulated it using more triangles or fewer triangles? Like, the simplest shape I can think of that would be a triangulation of a sphere would be if we only used 4 triangles to make like a 4-sided die, a very low resolution sphere, making the tetrahedron, right? What if we used that instead?
Well, you don't have to ask what if. Why don't you just calculate it?
Oh, right. I guess I could just do that. So a tetrahedron has 4 vertices, has the 3 on the base and then the 1 at the top, and 1, 2, 3, 4, 5, 6 edges and 4 triangular faces. That's why it's like a 4-sided die. So vertices minus edges plus faces would be 4 minus 6 plus 4, which is also 2. Okay, that's cool.
Yeah, and in fact, you could do the same calculation with each of the dice, which I should mention technically are called the Platonic solids. And if you do that, you'll always get 2.
Even if we used a 6-sided die, which was just a cube, it doesn't even have triangular faces.
Yeah, even for the cube, which you could do directly referencing the square faces. But the idea behind it is that you could always subdivide those square faces themselves into pairs of triangles. You just draw the diagonals in.
Oh, okay, I get it. And then what we would do is do the same thing to the torus. And if we get a 2, it means that these 2 objects are identical, at least topologically, right?
Well, unfortunately, it's not quite that straightforward. If we get the same number, it means they might be deformable one into the other. If we get a different number, however, then we know absolutely they are not equivalent to each other.
Oh,
yeah, it's a little more subtle than we might hope at first, but of course, the fact that it is more subtle and not quite so straightforward is what gives rise to the entire field of algebraic topology. That's very near and dear my heart. It's my own field. And there we say, hey, we need more tools. We better invent something because the Euler characteristic alone isn't enough. But getting back to the question of triangulating the torus, here's a neat way to do it. So I have these very cool math toys called polydrons, and they're plastic pieces that are shaped like regular polygons, and they have interlocking edges. So you've got equilateral triangles, squares, regular pentagons, and so on. And so by snapping the pieces together, you can make 3-dimensional shapes. And using just the equilateral triangles, I made a really nice model of a torus.
okay. And were you able to use that to calculate the Euler characteristic for the torus?
Yeah, I was. And this model, which by the way, has a very cool looking 5-fold symmetry to it, I ended up using 80 triangles in total with 120 edges and 40 vertices.
Oh, okay. Hang on. Let me calculate it. So let's see. It's vertices minus edges plus faces. So that'll be 40 minus 120, which is negative 80, plus faces, which is 80. So we get 0, which is different from the sphere, which was 2.
Right. We get a different value. And since the Euler characteristics are different for these 2 spaces, we know they are not topologically equivalent.
If it had come out at 2, that wouldn't really have given us anything definitive. It would have only told us it might be identical to the sphere. But the fact that it didn't come out at 2, we did get something definitive. It is not identical to the sphere.
Yep, you got it. The Euler characteristic is really very cool. It's a number, but somehow that number is sensitive to this underlying topological structure.
Okay, so if I understand this correctly, going back to the perfection pieces that we were talking about at the top of the show, every single one of those would produce the same Euler number because they are all topologically the same shape. But if we look at the letters that we were talking about a little bit later in the episode, those would not all give you the same Euler number. The ones that were in the same subgroups would have the same Euler number as each other, but letters that were in different subgroups might not.
Exactly. You've got it right on.
Awesome. Okay, so it's one thing to talk kind of abstractly here about looking at little letters on the page and can they deform into each other. But how does topology show up in the real world, in our day-to-day lives?
It actually doesn't.
Okay, well, that's our episode. Thanks for listening,
Right.
everybody.
Okay, so there actually are lots of applications out there, but I want to focus on a word you just said, and that word is abstractly. So topology is a very abstract discipline. However, having said that, I can think of one topological space in particular that lots and lots of people are interested in. And I'm talking about mathematicians and physicists and librarians and plumbers and poets and musicians and teachers and, well, everybody. And that space is the universe. It's the space we all live in.
Wait, the universe is a topological space?
Well, sure. It certainly can be modeled that way.
So what's its Euler number? Is it like infinity?
I have no idea. It's a good question, though.
That would be a lot of triangles.
Yeah, the idea that the universe can be modeled as a topological space has actually been the prevailing point of view since Einstein developed general relativity. But in that setting, there is a lot of additional structure. So we start with a topological space and then add to it a differentiable structure. So it becomes a manifold. To that, we add space-time, which gives a certain kind of metric to the manifold. There we can ask questions about curvature. And of course, Einstein was very interested in curvature because gravity is a way in which space-time gets curved. So which topological space is the universe? What is its Euler characteristic? I don't know. But I think a very interesting and fruitful question is, what can we learn about our universe by thinking of it in topological terms?
Wow, that really is interesting. And here's a thought. Now that I have a lot more understanding and context about topology, why don't you go ahead and tell me your joke again?
You think you'll get it this time?
I think there's a chance.
Okay. So, Noah, I've got a topology joke for you, and it goes like this. How can you tell that someone is a topologist?
I don't know how.
They can't tell the difference between a donut and a coffee cup.
See? Now I find it funny.
It's a very good joke.
Before we wrap this episode up, there's one more thing we still need to talk about. On our last episode, Dan from Math for Love challenged our listeners with this puzzle. Using only a fair coin, design a game that you have a 1 in 3 chance of winning.
And the reason this is difficult is because a coin flip can only result in one of two outcomes, heads or tails. So any game that requires, say, n coin flips has 2 to the n possible results. 2 to the n is a very even number. But when you make a fraction to show the probabilities involved, if the denominator is 2 to the n, there's just no way to put a whole number up top and produce a result of 1/3.
But that didn't stop you, Math Club. We got some really creative and ingenious solutions from several of you. The first person to submit a valid solution was David Radcliffe. Nice job, David. He said, toss a coin repeatedly until it lands heads. You win if the number of tosses is even.
Yeah, I really like this solution. Very, very clever.
Yeah, it might actually be a bit too clever for me. I know David is correct because Dan himself verified this answer as legit, but I'm not sure I understand the math here. Since half of all numbers are even and half are odd, it seems like you'd be equally likely to get your first heads flip on an even toss than on an odd toss. So what am I not getting here, Pete? Why is there only a 1/3 chance of getting your first heads on an even toss?
Yeah, we'll look at it this way, and admittedly, it's pretty subtle. So there are infinitely many different ways to win. You could throw tails, then heads, and win in round 2. You could throw tails, 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 and then heads, and win in round 4, and so on. This means the probability of winning is the sum of each of those infinitely many individual probabilities. So the probability of winning is equal to the probability of tails, heads, plus the probability of 3 tails followed by heads, plus the probability of 5 tails followed by heads, and so on. Well, this is an infinite series. In fact, it's a geometric series with ratio 1/4. The sum of the series is 1/4 plus 1/16 plus 1/64, and so on, converging to a value of 1/3.
Wow, that is tough to get my brain around, but I think I get what you're saying. That is a really clever answer. I also think we want to give an honorable mention to one other submission. Matt Enlow came up with the answer that Dan referred to as the slick answer when he was posing this question to our listeners last time. In Matt's solution, you flip the coin twice. If you get heads both times, you win. If you get 1 heads and 1 tails, you lose. And if you get both tails, it's a do-over. You flip again and then see what happens. And what's cool about this answer is it takes something that has 4 possible outcomes and all but eliminates one of them as a possibility. By making 2 tails a do-over, you make it so there are only 3 possibilities that result in a win or a loss. And so now you can have a 1/3 chance of winning.
Yeah, and notice in this example also, there is the possibility of infinitely many rounds, right? You could just keep getting the do-over outcome and play again, and play again, and play again. So there really is something fundamentally infinite about converting a 2 into a 3 or a 1/2 into a 1/3.
Yeah. So thanks to all of our listeners who submitted answers. We had a great time reading through them, and we passed them on to Dan, and he really did too. Before we go, would you like to tell our listeners how they can get in touch with us if they want to reach out with a question or a suggestion for a topic for a future episode or anything like that?
Sure, you can always send us an email. Our email address is mathclubpodcast@gmail.com. But listeners, I know you want to have a lot of fun, and we've been having a heck of a lot of fun over on our Twitter page. So why not stop by? Our handle is @mathclubpodcast.
Of course, topologically speaking, you'd probably say that our email address and our Twitter handle are identical.
Well, they do both have an @ and they do both have letters.
That's true. All right, Math Club, thanks for joining us. We will see you next time.
See y'all.